What if I told you that the chair you're sitting on, the phone in your hand, the very atoms that make up your body, none of it actually exists until something observes it? That sounds like the plot of a bad sci-fi movie. But here's the thing, it's not science fiction. It's physics. And the experiment that proves it has been run thousands of times over the last century with the same mind-bending result every single time. In 1978, a legendary physicist named John Archibald Wheeler proposed an experiment so radical that it seemed to suggest something impossible, that the act of observation doesn't just reveal reality, it creates it. And that observation can reach backward through time, determining what happened in the past. For decades, Wheeler's idea remained a thought experiment. But then physicists actually built it. And what they found shook the foundations of everything we think we know about the universe. This is the story of the delayed choice experiment, the experiment that proved reality doesn't exist until you look at it. And to truly understand why this matters, we need to talk about one of physics' greatest fighters, Leonard Susskind, the former plumber's son from the South Bronx, who would go on to revolutionize our understanding of observation, information, and the very fabric of reality itself. Let's start with a question that seems almost childishly simple. What is light? Is it a wave, like ripples spreading across a pond, or is it a particle, like a tiny bullet flying through space? For centuries, physicists argued about this. Isaac Newton was convinced light was made of particles. The Dutch physicist Christian Huygens thought it was waves. They both had good arguments, and for a long time it seemed like a question we might never answer. Then, in 1801, a British polymath named Thomas Young did something brilliant. He set up an experiment that should have settled the debate once and for all. He took a beam of light and shone it at a barrier with two thin parallel slits cut into it. Behind the barrier, he placed a screen to catch whatever came through. Now think about what you'd expect to see. If light were made of particles, tiny bullets, you'd expect them to fly through one slit or the other and create two bright bands on the screen. One behind each slit. Simple, right? But that's not what Young saw. Instead, he saw something bizarre, a pattern of alternating bright and dark bands stretched across the entire screen stripes, as if the light were somehow interfering with itself. This is exactly what waves do. When two waves meet, they can either reinforce each other, making a bigger wave, or cancel each other out. If light were waves, they would spread out from each slit, overlap, and create this interference pattern. Peaks meeting peaks would make bright bands. Peaks meeting troughs would create darkness. Young had his answer. Light is a wave, case closed. End of story. Except it wasn't. A century later, something strange happened in 1905. A young patent clerk in Switzerland named Albert Einstein looked at an odd phenomenon called the photoelectric effect, the way light can knock electrons out of metal, and realized that it only made sense if light came in discrete little packets. Particles. He called them quanta of light. We now call them photons. So wait, Young proved light is a wave. Einstein proved light is particles. Who's right? Here's the unsettling answer: both. Light is somehow both a wave and a particle. It's neither one thing nor the other until you look at it. And how you choose to look at it determines which aspect you see. This is what physicists call wave-particle duality. And it's not just a quirk of light. In the 1920s, scientists showed that electrons, actual matter, behave the same way. So do atoms. So do molecules. The quantum world is fundamentally uncertain, a realm of possibilities rather than definite realities. But here's where it gets really weird, and here's where our story truly begins. In 1927, two of the greatest physicists who ever lived, Albert Einstein and Niels Bohr, had a debate. Einstein couldn't accept this fuzziness. He argued that there must be some deeper reality, some hidden mechanism that determines what a particle is doing even when we're not looking. God does not play dice, he famously said. Bohr disagreed. He believed that quantum objects genuinely don't have definite properties until they're observed. The act of measurement doesn't just reveal what was already there. It brings one possibility into existence while erasing all the others. This became known as the Copenhagen interpretation of quantum mechanics, and it contains an idea so strange that even many physicists have spent a century trying to escape it. Reality is not real until something observes it. Now, you might be thinking that's just philosophical hand-waving. How could you ever actually test such a claim? That's exactly what John Archibald Wheeler set out to do. John Wheeler was one of the most creative minds in 20th century physics. He had worked with Einstein. He had helped explain nuclear fission with Niels Bohr. He coined the term black hole. And he had a gift for asking questions that made other physicists deeply uncomfortable. In the late 1970s, Wheeler became obsessed with the disturbing implication of quantum mechanics. If the act of observation determines whether light behaves as a wave or a particle, then what happens if you delay that choice? What if you wait until after the light has already passed through the slits, after it has supposedly decided how to behave, and only then choose how to observe it? Think about that for a second. In Young's double slit experiment, if you don't try to detect which slit the light goes through, you get the interference pattern. Light acts like a wave, spreading out and going through both slits simultaneously. But if you put a detector at the slits to see which one the light goes through, something remarkable happens. The interference pattern disappears. Light acts like a particle, definitely going through one slit or the other. It's as if the light knows whether you're watching. Wheeler's question was, what if you make the choice of how to observe, detector on or off, after the light has already passed through the slits, after it has already decided to act like a wave or a particle? If the Copenhagen interpretation is correct, the outcome should still depend on your choice, even though that choice happens after the light has committed to its path. This seems to imply something impossible, that your present choice can reach backward in time and determine what happened in the past. Wheeler took this idea even further. He imagined a cosmic version of the experiment. Picture light from a distant quasar billions of light years away. That light, traveling through space for billions of years, encounters a galaxy along the way. The galaxy's gravity bends the light, acting like a giant lens. Some of the light curves around one side of the galaxy, some curves around the other. When that light finally arrives at Earth, we have a choice. We can set up our experiment to let the two paths combine, revealing an interference pattern, proving the light traveled both paths simultaneously like a wave. Or we can set up detectors to determine which path the light took, revealing particle behavior. Wheeler's claim was staggering. Our choice today, right now on Earth, determines how that light behaved billions of years ago, before our planet even existed. Now, Wheeler was very careful about what he was saying. He wasn't claiming we could send messages backward in time or change the past in some sci-fi sense. What he was saying was more subtle, and in some ways more disturbing. The past doesn't have a definite character until it's observed. History itself is not fixed until we measure it. As Wheeler put it, the past has no existence except as it is recorded in the present. For decades, this remained a thought experiment. The technology to actually test it didn't exist. But Wheeler's idea haunted physicists, because if he was right, it would mean something profound about the nature of reality itself. Now, to understand why this matters, and why a physicist from the South Bronx named Leonard Susskind would spend his career grappling with these same questions, we need to understand what's actually happening in the quantum world. The standard picture goes like this. A quantum object, a photon, an electron, whatever, exists in what's called a superposition. It's not in one state or another. It's in a fuzzy combination of all possible states simultaneously. Only when you measure it does it collapse into one definite state. But here's the question nobody could answer. What is a measurement? What is an observation? Is there something special about consciousness? Does the universe somehow care whether a human is watching? This is what physicists call the measurement problem, and it's been arguably the deepest puzzle in physics for 100 years. In 1984, scientists at the University of Maryland actually built Wheeler's delayed choice experiment in a laboratory, and they found exactly what the theory predicted. Inserting or removing the detector at the last moment changed whether interference was seen, even though the photon had already passed through the slits. In 2007, a team led by physicist Alain Aspect, who would later win a Nobel Prize, performed an even more refined version. The results were the same. The observer's choice made after the fact determined the photon's behavior. In 2015, researchers at the Australian National University did the experiment with single atoms instead of photons, same result. And in 2025, MIT physicists performed what they called the most idealized version of the experiment ever, using individual atoms as the slits themselves and single photons as the test particles. They confirmed, once again, that the more information you obtain about which path the light took, the more the interference pattern fades. The act of knowing destroys the wave. Every single time, the experiment confirmed Wheeler's bizarre prediction. Our choice of how to observe determines what we see, and it doesn't matter that we make that choice after the fact. But here's the twist, and this is where it gets really interesting. The delayed choice experiment doesn't actually prove that we're changing the past. It proves something even more unsettling. The past never had a definite character to begin with. This brings us to Leonard Susskind. Born in 1940 in the South Bronx, Susskind grew up in a working-class family. His father was a plumber. Nobody expected him to become one of the most influential theoretical physicists of his generation. But his father saw something in him. As Susskind later recalled, his father told him, "You ain't going to be no engineer. You're going to be Einstein." Susskind earned his physics degree from City College of New York and his PhD from Cornell. And over the following decades, he would co-invent string theory, pioneer the holographic principle, and wage a legendary intellectual war with Stephen Hawking about the nature of black holes. But throughout his career, Susskind kept returning to a fundamental question: what does quantum mechanics actually tell us about the nature of observation and reality? In 2016, Susskind published a remarkable paper with the provocative title Copenhagen via Everett Teleportation and ER EPR. In it, he directly confronted the measurement problem that the delayed choice experiment reveals. His conclusion was blunt. As Susskind wrote, "It is obvious that the Copenhagen interpretation cannot be the last word. Here's why. The Copenhagen interpretation requires a special entity called the observer, something outside the quantum system that performs measurements and causes collapse." But as Susskind pointed out, this makes no sense when you think about the universe as a whole. The universe is filled with subsystems, any one of which can play the role of observer. Susskind argued, there is no place in the laws of quantum mechanics for wave function collapse. The only thing that happens is that the overall wave function evolves unitarily and becomes more and more entangled. Let that sink in. According to Susskind, wave function collapse isn't real. It's an approximation, a shortcut we use because we can't track all the quantum entanglements in the universe. The universe is an immensely complicated network of entangled subsystems, he wrote, and only in some approximation can we single out a particular subsystem, as Tho Sarvar. This connects to one of Susskind's most profound contributions to physics, the holographic principle. In 1994, building on ideas from Dutch Nobel laureate Gerard 't Hooft, Susskind proposed something that sounds almost insane. The three-dimensional world we experience is actually a kind of projection. All the information in our universe, every particle, every force, even space and time themselves, can be encoded on a two-dimensional surface like a cosmic hologram. As Susskind put it, the three-dimensional world of ordinary experience, The universe filled with galaxies, stars, planets, houses, boulders, and people is a hologram, an image of reality coded on a distant two-dimensional surface. Now, how does this connect to the delayed choice experiment? Here's the key insight. In the holographic picture, information is fundamental. The universe isn't made of stuff in the conventional sense. It's made of information. And the way that information is organized depends entirely on how you divide the universe into observer and observed. Susskind showed this most dramatically in his work on black holes. In 1993, he proposed the idea of black hole complementarity. When something falls into a black hole, there are seemingly two incompatible stories about what happens. To someone outside, the object gets smeared across the black hole's horizon and eventually radiates away. To someone falling in, nothing special happens at the horizon. They sail right through. Both stories are true. Both are valid descriptions of reality. But no single observer can ever see both. It depends on your perspective. It depends on how you observe. This is quantum complementarity taken to its logical extreme, and it's exactly what the delayed choice experiment shows. You can see wave behavior or particle behavior, but never both. The reality you observe depends on the experiment you perform. But Susskind went further. In 2013, working with his colleague John Maldacena, one of the most brilliant physicists of his generation, Susskind proposed an idea that unifies these themes in an astounding way. They called it ER EPR. In 1935, Einstein published two papers that seemed completely unrelated. One was about wormholes, theoretical tunnels through space-time that connect distant points. These are called Einstein-Rosen bridges, or ER bridges. The other paper was about quantum entanglement, the strange phenomenon where two particles can become correlated so strongly that measuring one instantly affects the other, no matter how far apart they are. This was the Einstein-Podolsky-Rosen paper, or EPR paper. For nearly 80 years, nobody saw a connection between these two ideas. Then Maldacena and Susskind proposed something extraordinary. These two phenomena are the same thing. Every pair of entangled particles is connected by a tiny wormhole. Entanglement I is a wormhole. ER equals EPR. Think about what this means for the delayed choice experiment. When a photon passes through the double slit apparatus, it becomes entangled with the measurement device. According to ER EPR, this means tiny wormhole-like connections form in space-time itself. The geometry of reality shifts depending on what entanglements exist, which depends on what measurements you perform. In this picture, it's not that your observation collapses the wave function. It's that your observation determines the space-time geometry itself. The past isn't fixed because space-time connections are constantly being rewritten by entanglement. This is what Wheeler intuited 50 years ago when he proposed the delayed choice experiment. He called it the participatory universe, the idea that observers don't just passively watch reality unfold, they actively participate in creating it. As Wheeler said, we are participators in bringing into being not only the near and here, but the far away and long ago. Susskind's work gives this intuition a mathematical foundation. In his framework, observation isn't something mysterious that exists outside of physics. It's entanglement. It's geometry. It's the very structure of space-time, and that changes everything. Now, you might think this resolves the mystery, but physics is never that simple, and Susskind has spent decades battling over what these ideas actually mean. The most famous battle was with Stephen Hawking. In the early 1980s, Hawking made a disturbing claim about black holes. When matter falls into a black hole and the black hole eventually evaporates through Hawking radiation, the information about that matter is destroyed forever. Gone. Erased from the universe. This might not sound like a big deal, but it's actually catastrophic for physics. Here's why. Quantum mechanics is fundamentally about information. The wave function contains complete information about a system, and one of the sacred principles of quantum mechanics is unitarity, the idea that information is always conserved. You can scramble it, hide it, spread it around, but you can never destroy it. If Hawking was right, black holes violate unitarity. They destroy information. And that would mean quantum mechanics itself is wrong at some fundamental level. Susskind refused to accept this. I thought Hawking had lost his mind. Susskind later said, what followed was a 28-year intellectual war. Hawking on one side, insisting that information is destroyed. Susskind on the other, convinced it must be preserved. This wasn't just an abstract debate. It went to the heart of what we mean by reality. If information can be destroyed, then the past is genuinely erased, not just uncertain, not just undefined, but gone, deleted from existence. If information is preserved, if Susskind was right, then in some sense, everything that ever happens is recorded somewhere. The universe keeps track. Reality is coherent. In 2004, at a conference in Dublin, Hawking conceded. He admitted he was wrong. Information is not destroyed by black holes. The universe is unitary. Quantum mechanics survives. Susskind had won the black hole war, but the victory came with a strange implication. If information is preserved even when something falls into a black hole, where does it go? How can it be both inside the black hole and encoded on its surface, ready to be radiated away? This is where black hole complementarity and the holographic principle come in. The information is both inside and on the surface, depending on who's observing. Just like in the delayed choice experiment, the answer depends on how you ask the question. The debate didn't end there. In 2012, a group of physicists at UC Santa Barbara, Almiri Marolf, Polchinski, and Sully, known as AMPS, threw a bomb into the discussion. They argued that black hole complementarity leads to a paradox. You can't have smooth passage through the horizon and preserve information and avoid faster than light signaling. Something has to give. Their solution was a firewall, a wall of high-energy particles at the black hole horizon that would incinerate anything falling in. This would destroy complementarity and Susskind's picture along with it. Susskind fought back. In a series of papers, he argued that the AMPS paradox is really about computational complexity. Creating a firewall would require an observer to perform calculations so astronomically complex that they would take longer than the age of the universe. The paradox is theoretically possible but practically impossible. In other words, the rules of quantum mechanics are consistent, but some questions are simply too hard to ask. This connects back to the delayed choice experiment. The reason we can't catch reality in a contradiction, the reason we can't see both wave and particle simultaneously, isn't because of some mysterious collapse. It's because the entanglements required to see both are mutually exclusive. The information architecture of the universe prevents it. Susskind is now in his mid-80s. He's still publishing papers, still pushing boundaries. His recent work on de Sitter space, the geometry of our accelerating universe, suggests even more radical conclusions. In a 2021 paper titled "Three Impossible Theories," he argued that quantum gravity in our kind of universe may be fundamentally impossible to formulate in the usual way. We may need entirely new conceptual frameworks. The delayed choice experiment opened a door in 1978. Nearly 50 years later, we're still exploring what's on the other side. So what does all of this actually mean? What does the delayed choice experiment and Susskind's decades of work building on it tell us about reality? Here's what we know for certain. First, quantum mechanics works. Every version of the delayed choice experiment ever performed confirms the predictions of quantum theory. Whatever is going on, quantum mechanics describes it accurately. Second, naive realism is wrong. The idea that there's a definite reality out there, independent of observation, that particles have definite positions and properties even when no one's looking, is not supported by these experiments. The evidence points to something more subtle. Third, observation matters, not in some mystical consciousness is magic sense, but in the precise mathematical sense that how you set up an experiment, what entanglements you create, what information you extract, determines what you see. But here's the deeper point, and this is where Susskind's contributions become crucial. For decades, physicists talked about observation and measurement as if they were something outside physics, as if consciousness somehow stood apart from the physical world and collapsed wave functions by looking at them. Susskind's work shows that this isn't necessary. Observation is just entanglement. When you measure a system, you become entangled with it. And entanglement has physical consequences. It affects space-time geometry. It determines what information is accessible. It shapes what we call reality. In this picture, there's no need for a special observer outside the system. Every particle, every field, every corner of the universe is constantly observing everything else through entanglement. The universe is, as Susskind wrote, on an immensely complicated network of entangled subsystems. Wheeler called this the participatory universe. He believed that the universe isn't just out there, waiting to be discovered. It's being created moment by moment through countless acts of observation. As Wheeler put it, we are not simply bystanders on a cosmic stage, we are shapers and creators. But Wheeler went even further. He proposed an idea called, from bit, the notion that physical reality emerges from information bit. Every particle, every field of force, even space-time itself derives its existence from answers to yes or no questions. Susskind's holographic principle is, in some sense, a mathematical realization of Wheeler's vision. If all the information in a three-dimensional region can be encoded on its two-dimensional boundary, then information truly is fundamental. Reality is information structured by the patterns of entanglement. Now, you might be wondering, does this mean the universe isn't real? Does this mean nothing exists unless we're looking at it? Not quite. What it means is that existence is more subtle than our everyday intuitions suggest. Think about it this way. Before you open your refrigerator, is there food inside? Common sense says yes, the food exists whether you look at it or not, and at the level of everyday objects, that's effectively true. The food is constantly being observed by the air molecules around it, by the light bouncing off it, by the refrigerator itself. Everything is entangled with everything else. Macroscopic objects don't show quantum weirdness because they're constantly entangled with their environment. But at the quantum level, where systems can be isolated from their environment, the situation is different. A single photon heading toward a double slit really is in a superposition of going through both slits. It really doesn't have a definite path until something becomes entangled with it in a way that records path information. The delayed choice experiment shows that this indefiniteness extends backward in time. The photon doesn't retroactively change its past. Rather, its past was never definite to begin with. History crystallizes only when information is extracted. This is a profound shift in how we think about reality. The universe isn't a cosmic movie that was filmed in advance and we're just watching the playback. It's more like an improvised play where each act of observation contributes to writing the script, including the parts that seem like they happened before the observation was made. Leonard Susskind grew up in the South Bronx. His father was a plumber. Nobody expected him to spend his life wrestling with the nature of existence. But physics has a way of finding people who refuse to accept easy answers. Throughout his career, Susskind has been driven by paradoxes, by situations where different principles of physics seem to contradict each other. Quarks that exist but can't be extracted, black holes that seem to destroy information, observers who see different realities depending on where they stand. Each time, the paradox led to a deeper understanding. Quark confinement led to string theory. The information paradox led to the holographic principle. Black hole complementarity led to ER EPR. And all of it traces back to the central mystery revealed by the delayed choice experiment. That observation and reality are not separate things. They are intertwined in ways we are only beginning to understand. Susskind once said something that captures the spirit of this journey. I do take 100% seriously the idea that the world is a figment of the imagination. That's not nihilism, it's humility. It's the recognition that our concepts of reality and existence, forged in the everyday world of chairs and tables and refrigerators, may not apply to the quantum level. The universe is stranger than we imagined, and we're only at the beginning of understanding how strange. The delayed choice experiment doesn't just tell us something surprising about photons. It tells us something surprising about the nature of time, causality, and existence itself. The past is not fixed. Reality is not predetermined. The universe is not a machine running according to a preset program. It is, instead, what Wheeler called it, a participatory phenomenon. A collaboration between what exists and how it is observed, a dance of information and entanglement that creates the fabric of space-time itself. After more than 5 decades of grappling with these mysteries, Susskind is still at it, still publishing, still teaching at Stanford, still asking questions that make younger physicists uncomfortable. Because that's what physics does. It takes you to the edge of the knowable and forces you to stare into the abyss. And sometimes, if you stare long enough with enough courage and honesty, the abyss reveals something beautiful. Reality doesn't exist until observed, and in some strange, deep way, that's the most real thing we know.